abbreviated online version of the ESIG Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we canceled the physical meeting in Tucson due to the coronavirus situation, and we decided to proceed with a shortened online version. We started the series of 12 webinars in mid-March, and we're running through early May approximately twice a week. You can find the full schedule at the ESIG website under the Events tab. Recognizing the limitations of a webinar with typically more than 100 people on the line, we will have individual presentations of 10 to 15 minutes, followed by a few minutes of discussion moderated by the session chair, with hopefully some time for discussion at the end. The lines will be muted, so we will ask you to use the question box in the lower right-hand corner of your screen. Today, we'll be hosting session 7 on sector coupling and flexibility, chaired by William de Hasler. William is a professor in the Department of Mechanical Engineering at KU Leuven in Belgium. He is currently head of the Interdisciplinary Energy Institute, where his current interests include energy systems integration, long-term storage, energy systems optimization, decarbonization, nuclear energy policy, and market design. William is truly a Renaissance man. He's an active member of the ESIG Board of Directors and a good friend of ESIG. William, I'll now turn it over to you.
Thank you, Charlie, for this introduction. Well, welcome to everybody to this session on sector coupling and flexibility. I wrote down a few thoughts on paper, so if you forgive me that I look a little bit downward here. As a matter of fact, this session on sector coupling and flexibility is a nice follow-up of the session of last Tuesday on integrated energy system analysis. To some extent, that session of last Tuesday could be seen as an introduction for the current session. Now, how do I see this whole issue? I'd say that most players in the energy theater these days accept that we are living through a most challenging energy transition with the ultimate goal to fully decarbonize the overall energy system. And historically, well, actually, I would say the last 10 to 15 years or so, we've started out with the electric power system where it became clear that we needed more flexibility to cope with the consequences of the naturally fluctuating renewables, or variable or intermittent renewables, as you wish to call them, to balance supply and demand of electrical power. Now, one of the flexibility options besides thermal plant cycling, storage, extended transmission, and curtailment is demand response. And one particular type of demand response is to consider interaction with the other so-called sectors, such as transportation and the heating sector. So residential, services, and commercial, and also industrial. Now, if we take that actually one step further, in a broader perspective, we can also consider interaction with the overall industry sector, not only for heat, but also for the other carriers and even feedstock. Now, this is often, especially in Europe, called sector coupling, but as said, it is actually nothing else than demand-side participation in a broader sense. As far as I'm concerned, there are two ways of looking at this issue of sector coupling for flexibility, one with a negative connotation and another one with a positive connotation. The negative one goes as follows. Over the last so many years, we have managed to massively perturb the electric power system by introducing large amounts of variable or intermittent renewables into the system. In order to obtain a large renewable electrical energy share, a substantial amount of overcapacity is expected, and hence we need extra demand to dump the superfluous electrical power, etc., etc., etc. However, there is also a positive way to look at this whole thing, and the positive way takes advantage of what has been going on. Of course, it takes advantage of what is going on in the electric power sector, but it considers the renewables overcapacity of variable renewables as kind of an opportunity. Indeed, the heating, transportation, and by extension the industrial sectors are very difficult to decarbonize. Thus, integrating these sectors with the electricity sector opens a possibility that were not realistic before. And in places where molecules remain the preferred option, the interaction with the electric system may provide an interesting option to produce synthetic fuels, starting from electrolysis, then go through hydrogen, maybe methane, and up to liquid fuels, etc. But anyway, this is only the introduction. I'm just sketching the overall philosophy, the way I see it, but more of these elements will clearly be discussed by our speakers today. Now, compared to the original program, regrettably, we only have 3 presenters today. Bernie Ernst, who was supposed to discuss the transportation sector, had to decline at the last moment because of unexpected circumstances. But looking at it from the bright side, that allows the other speakers to dive a little bit deeper than originally foreseen, if they really think that is necessary. Now, please aim for 15 minutes, but if you really feel the urge to go a little bit longer, well, I will allow that. We will start first with Christopher Clack, taking a first look at the overall system modeling and optimization of system integration. Then Elizabeth Endler will come in, and she will discuss flexibility in industrial production. And finally, Michael Baldea will look more specifically at flexibility improvements from process engineering. So let's get started with the first presenter, Christoph. I'll just read some lines of his bio here. So Dr. Clack is CEO of Vibrant Clean Energy, and he's pursuing a path that leads the way to more intelligent electric power system design here in the US and abroad. Well, I would say there in the US and abroad. Now, Dr. Clack has been at the forefront of the energy optimization world for many years. In 2012, he created the groundbreaking National Energy with Weather Systems, NEWS, a simulator with a principal investigator, while a principal investigator for a National Academy of Sciences National Research Council project. He later transferred to the Cooperative Institute for Research in Environmental Sciences, CIRES, at the University of Colorado Boulder. And during his time at CIRES, he developed various methods to advance the way people think about variable generation and the future role it has. He can be characterized as an expert in mathematics, statistics, and optimization. He combines this expertise with the gained skills of numerical weather prediction, electrical engineering, and economics. Christopher, you have the floor, please.
Thank you very much for that introduction. So what I'm going to go through today is going to spend a bit of time kind of going over how I think about the problems and how we think about them at VCE to kind of this sector coupling paradigm that we're talking about, and how we are extracting information from that to look at different scenarios for the US. We've extended it to Europe recently, but we can't share those results just yet. But the same underlying principles apply. Of course, the nuances in the detail, but we're going to show one example of deep decarbonization in the US when we look at all the sectors being coupled together. So just as a broad overview, this is kind of exactly what William was talking about just now. Is like the electricity sector is just one aspect of the whole economy, of course, and we have gone a long way to reducing emissions in that sector around the world. But other sectors are still very high and actually growing. And in the US, transportation is now bigger than electricity. And so what we think of as a paradigm is how we can couple these together. And the way I think of them, and we did this in a paper in Science in 2018 with a lot of co-authors, is how do these sectors connect together, and what do we need to model to sort of bring them together and use them? And so we have the electricity, which is electrons, The easiest next coupling sector is hydrogen to connect to various other areas. One is obviously power to gas, which allows for the electricity flexibility area. The other is to produce hydrogen to then produce ammonia and other synthetic fuels, which can be used for both agriculture and also aviation. And then there's a final sort of area that we look at and think about is also direct capture of the CO2 as well, to close that final last few percentage points of the energy economy. And so this is kind of a broad overview. It's very simplistic, of course, it's not capturing every single last aspect, but it kind of gives you a framing of how I think of the problem and how wisdom has started from VCE, started in the electricity sector and is sort of broadening out to all the other sectors. So we model now everything in the four colors. So green first, then blue, then purple, which is the synthetic fuels, and then finally the red for direct capture of the emissions themselves. So the way we think about electrification, or the way I kind of conceptualize it in my head, is one is we electrify by directly providing electrons for other sectors. And then there's a fifth one, so that's light duty vehicles, heavy transportation, and then heating and both space and water, as well as electrifying cooking, which we would call a traditional demand, but obviously removing gas hobs to electrifying them will change the profile of that electrification. The fifth one's kind of a big one, which is hydrogen, which unlocks quite a lot of other areas. I still think of it as electrification. We're just adding an additional step, which is to then use hydrogen as a stable chemical bond to actually transport around or use for other areas where heat is either required or we actually need the hydrogen itself, for example, in ammonia or in producing steel. We actually want the hydrogen, not the heat or energy, or both. And so we use this to blend with other sectors. So some people may not be able to get a space heat pump in their climates, and so we may want to use hydrogen to not have that be electrified fully. We do this, and I just want to note at the end, we do this kind of in the backdrop of we're also considering what climate is actually doing to all these sectors as we move forward in time. So one thing that we've added recently and been thinking about a lot is we have used a lot of historical data, and we continue to use historical data, but the future keeps changing. And depending on what path we're on, it might change very much how much we can rely on, say, heat pumps for heating versus needing hydrogen for heating demands. And I'll get onto that in a little bit towards the end. I don't want to go too deep into it. What we see is by 2050, if we electrify the other sectors, we're looking at almost a doubling of the peak demand by 2050. And what I mean by a doubling is that I don't know when that peak is going to happen, but I know that the amount of compounding electrification that's happening is meaning that the peak will be 92% greater by 2050. And the other thing to note on this graph is that it's very kind of shallow to 2030, and then it gets very, very steep after 2030. And that's because when we've been modeling it, we kind of have this lag of changing things on the system, and so it takes time to actually increase the peaks. So what does it look like when we sort of look at it in terms of energy rather than just the capacity, I guess, is the way of looking at it. We started around 3,800 terawatt hours, and again you can see that kind of shallow rise, and then sort of it inverts in 2030 where we really start accelerating. So part of that is the model meeting electrification goals in the early years, but also that we're building out systems within the electricity sector to reduce emissions there as well, that then unlocks the potential later on for the next 20 years to really drive up electricity demand. And so in the electricity demand area, we're seeing a doubling of the number of electrons needed for the customers. And so that's quite a large increase. And this is basically reaching around a 95% decarbonization of the electric sector. Sorry, 95% decarbonization of the energy sector by 2050. So I just wanted to break down a few examples here so we can kind of see what I'm talking about when I talk about the different demands. So this is 4 states in the US, and what we did is we just plotted the normalized demand of what we call the traditional demand. So the traditional demands are things like industry, cooking, TVs, lighting for each of these states. And they are broken down more and more in the model, but just to give you kind of an overview. And the way we're displaying it here is the sum of these curves equal 1 or 100%. And so if we multiply by the annual demand in the state, we'll get the actual electricity consumed. And the 4 that I have, at the top left is New York, top right is Florida, bottom left is California, and the bottom right is Minnesota. And the reason I want to show this is just how different these shapes look when we bring the weather in. So these are simulated demands, but they're also tied to realities of what happened in the weather years that we're looking at. And we've stripped out any heating or transportation that's already in the electric sector because they're going to be modeled separately. And Florida looks very different to New York, which looks very different to Minnesota. And so already we're going to start seeing things change as we push forward through time in different states if the load grows at different rates. This next one is showing what the heating demands look like. And now these are fractional again, and the sum is 1 again. And so things like New York and Minnesota have much more stable energy needs for heating. And what I mean by that is you still need some more in the shoulder seasons than you do in, say, Florida, where once you get into the summer season, you don't really need any heating demand at all for space. And so the winter peaks look larger. But again, when you multiply by the actual energy consumed annually for the heating, Florida still has a lower number. It just means the variability is higher. And again, we have this for each state and each county, in fact. And what we're doing here is we're tethering these to the electrics, to the weather as well. I'm going to show you the same thing here for heating. I won't go into too much detail here, but you can see each of the states is more similar now. And that's because the heating, for water heating, most of the technologies we use are very efficient. They're also well insulated, and so the differences aren't as big. But as you can see, there are differences even in those regions as well. And then finally, looking at transportation loads, we bring in a bit of social behavior here as well, how people drive, how much activity there is in the transport sector. I'm going to caveat everything right now with, what's happening now in COVID-19 is going to be something that we're going to have to investigate a lot as a society in terms of how that will change the demands, both near term, but also how it might change things going forward. Maybe things will change, maybe they won't, maybe they'll just rebound back. But for certain, the transportation, we've been using historical data on how people move around at different times of the year for different regions. And I think that's going to change in at least the short term as well. So if I sort of bring this all together, what does this really mean? So I've shown you kind of the load shapes, but they're normalized, so they don't really mean much. So what I'm doing here is I'm going to show the aggregate over the whole of the contiguous US through time. So this is a 2020 sort of snapshot of what we estimate the load will look like. So we have a summer peak of around 750-ish, and we have a winter peak of around 620. And then if I go to 2030, we see things sort of jump up. The winter is now kind of 700, the summer's around 700 or so as well. Then when we go to 2040, we see a much bigger jump. And remember, I was talking about how the sort of the energy takes off quite a bit. And now we're over a terawatt in winter, and we're just slightly shorter than a terawatt in summer. But now we're kind of seeing a dual peak system. And hopefully you can also see that we're getting a bigger variability throughout the days as well and the weeks. And so then to 2050, we're now seeing the whole US being fairly substantially dominated by winter peak because we have all that heating that we need. But then we do also have a summer peak as well, but it's just not as high. And of course, regionally, this looks different, but we're kind of seeing the aggregate now of all these different areas come together, as well as predicting or kind of estimating what the actual energy consumption will be, as well as those normalized shapes. For all this, we kind of want to bring in like detailed wind data sets for both the resource siting, but also how it then co-varies with these new loads that are coming in. Wind, for example, will be very highly correlated to space heating and water heating. And so we really want to be able to kind of look at how they correlate and are anti-correlated, and how they then work together with other technologies that are also on the grid. Like, for example, if we have to transport it, is the transmission constrained for some reason? Do we need to build more than we think we do? And aspects like that. But we need to be able to see geographically and then temporally how these sort of co-oscillate and how they work together in tandem. And again, of course, our data sets will include the solar as well and how that might interact as well for that summer peak. But because we're now looking at that big winter peak, it really starts being a situation of the wind and solar actually needing to blend together, because there's this divergence between summer and winter for solar and wind that are kind of very complementary in this paradigm. The reason I go on about the sort of hourly and sub-hourly detail is that it really matters when you're trying to heat a home, for example, with a heat pump, what's going on at a high resolution, because now the model is trying to think about how the demand flexibility might interact with the grid, because these new demands are actually more flexible, but there's constraints on those. If the temperature would drop too quickly, if the heat pump was turned off, for example, the model needs to know that it can't do that, and so it has to bring in this high temporal data to know how it can capacity expand at the large scale as well. And what I'm just showing here is for New York State, just a kind of historical look at the wind and solar in that state, both annually, which is on the left for each hour, and then on the right, I've just zoomed in to a short period to kind of show how the oscillations in the wind are much slower moving than the oscillations in the solar. And I know it's not hugely easy to see on these plots, and hopefully when it's uploaded, it'll be easier for people to see. Okay, and then I just wanted to mention that the storage behavior is kind of important, how that changes both long-term and short-term storage, because they really will impact how these variable generations might come in. And when I talk about storage, I'm talking about both battery storage, but also chemical storage through hydrogen and other technologies for longer-term storage. And all we're showing here is an example of how the Wisdom model is kind of absorbing curtailed energy and dispatching it when the VREs drop down. And I've deliberately kind of co-located the scale so you can kind of easier track the greens, which is the VRE, and then the orange, which is the storage output. And hopefully you'll see each time the renewables start dropping, the storage peaks up above the zero line. And to do this integration, we need to start with the electricity grid we have. On the left, we have the capacity, and on the right, we're just showing where they're geolocated. I don't want to spend too long on this, but we kind of have to start with the grid we have. And what's really important for electrification is the grid topology. And the reason we need the grid topology is these loads that are being added are going to be added in places that we may not have seen load growth for a very long time. Residential areas, commercial areas where we kind of have a good prediction of what the loads are going to look like. But actually, as we push forward, these loads are going to get really big pockets. And I've zoomed in again on the Northeast here. But if I zoom in further into New York, at the bottom, we see the topology of the transmission grid. And how it might be constrained, and then the generation and how on the top right of how it's sort of spread out across the state. And you can see kind of easily there'll be a bottleneck near the New York City area for getting energy to that. And if we electrify large swathes of the other sectors in that city. There's going to be pockets of very expensive distribution build out, as well as other areas that may be mitigated with other technologies like DERs, making it more flexible, maybe behind the meter storage, sort of reducing those peaks so that we don't have to build as much transmission to come into one load center. Finally, in terms of sort of data sets that we really need to think about for looking at electrification, coupling the sectors, is climate change. As we add more and more sectors in, climate change will have a bigger impact on, let's say, electricity, because if we're relying on 60–70% of the economy to be powered by electricity by one way or another, we need to know how climate might impact each area of that. And so I've just kind of listed out what I think, what we think is kind of the big areas. Demand profiles, how they change. The wind and solar supply is a very important change, particularly if we have high renewable standards. The water supply for thermal generation and hydroelectric is another area that really needs consideration in terms of how it might cause unforced outages and how other things might change in terms of the heating of the water. The transmission line rating and line losses is kind of a big one as well. We build lots of renewables that are remote. How do we ship them? Do the line ratings get derated too much in a high CMIP 5 scenario, or can we find ways to ameliorate that? And we have the same thing for heat rates and for the flexibility of the load profiles as well. As we change the climate, we may be able to make it easier or harder to change the profile of the demand. And so all I'm showing at the bottom here is how the wind has changed. Red is an increase in wind, and blue is a decrease. This is an average over that year, 2020 and 2050. Left is 2020, right is 2050. But the increase that you see in the plains looks good, and it is because it happens at night. And so if we have electrification, it's good. If we don't have electrification, it's even worse than before, because we have the bigger divergence between night and day than we've had before. Just to quickly look at a few other areas. On the top left, we're looking at the solar changes. Predominantly, the south gets more solar, and the north gets less solar, and that's partly because of more clouding that occurs. The top right is the heat rates. We're seeing an increase in heat rates in the middle of the day, 10–20% higher heat rates, which has consequences on fuel burn and emission as well. The bottom left is showing how the space heating is actually being squashed by climate change, because we don't need as much space heating, which is a smaller impact than the increase in cooling, unfortunately. And then the bottom right, we're showing the EV charging changes, how that behavior might change based on the amount of energy that might be needed to move around. So that's kind of I know there's a lot there, and I've kind of gone into a bit of detail, but I kind of want to sort of give an overarching kind of understanding of these things, how they come together. They may be beneficial, but we have to be considerate of the constraints that are then applied as well. And then how they link together is really important. How they superimpose on top of each other is where the benefits really start to come out. So I'm just going to show a quick example here. I'm not going to spend long on it because I know I've taken a bit too much time. But I wanted to show the results of an internal study looking at deep decarbonization of the CONUS. This is going forward through time, 2018 to 2050, and the different technologies are kind of stacked. This is capacity on the grid. The left shaded bar is the original demand, peak demand, and the right shaded is the new demand. The model picks that new demand. So the model is having the flexibility of those new sectors come in and participate in markets, and maybe you don't have to build as much capacity as you first think. And what you'll see is there's around 2/3 renewables and 1/3 other stuff. And that other stuff composes of different nuclear technologies as well as CCS technologies, enhanced geothermal technologies. And there is a small amount of gas left in this. This achieves a 95% reduction in economy-wide emissions by 2050. And so this gas here, although traditionally we might say we don't want any gas by 2050, but actually we've removed it out of other sectors which are less efficient and actually have made it be more concentrated, which then if we wanted to do something like CCS or DAX, we could make it more economical. If we look at it as the state breakdown, this is what 2018 looks like, and all I wanted to show was just kind of how it changes to 2050. So I'm just 2018 here. In 2050, changes things quite a lot. And the reason it changes quite a lot is that we have a lot of new technologies coming in. A lot of wind and solar is really participating in this new grid. And what that means is there's new technologies that are absorbing and using that power. This is kind of just trying to kind of show how the US would change by 2040. I'm not showing 2050 here because there's a lot more novel technologies that come in by 2050. But by 2040, hopefully, compared to our earlier plots, you can see there's a lot of change going on. We have a lot more offshore wind. The onshore wind has got more diverse. It's spread out more across the country. And the yellow, which is green, by the way, blue offshore. Yellow is storage facilities that are being built. So hopefully you can see that's a new thing. And then the pinks are sort of novel technologies that are being installed around the US as well. And all I'm trying to show here is that where you looked at those capacity maps earlier for wind and solar, you'll notice there isn't as much wind and solar in these few states in the central plains here. And that's partly because of the transmission needs, but it's also partly because the new sectors coming in actually allow you to have renewables closer to the demands than you may traditionally think under the current electric sort of paradigm. We do need transmission, of course. I think that's going to be a recurring theme through all energy needs. If everything flows through electricity, which it's looking like it may need to, the linchpin and all that is building some transmission. We really need more transmission being built, and it'll make everything easier, particularly if we're going to be relying on more of the economy being supported by electricity. I just want to show the emissions here and how they kind of fall in the electric sector. And so we get a 99% roughly reduction in the electric sector by 2050. And that gas is mainly there for backup and peaking capacity. To show that as a generation share of resources, what you'll notice is around half of the energy comes from renewables and around half from other technologies. We've done other studies where we've looked at just renewables and how that might look different. And I've talked about that before, so I don't want to repeat that here. But basically, we see the share flattening off around 50, 60%. And that's predicated on the fact that we're electrifying and we're actually increasing demand a lot. So 60% of 7,000 terawatt hours is more than the demand is today. And so we're producing a lot of renewables here. These other technologies are kind of coming in there because we're needing to firm up the capacity needs in this particular scenario. I just wanted to show a close-up of the dispatch before closing out to kind of show how the model is using both scales, the short-term and the long-term, to kind of decide how to build capacity needs and how to build storage and other technologies. And so this is a snapshot of the whole contiguous US in 2020. There's a black line at the top, which is what we call the altered load. And underneath it, there is actually a dotted line, which is the original load. So DSM is playing a part by 2020, but very little. And you can barely notice it. And hopefully here you can see the different technology colors stacked up. If I now move to 2050, this is the same time period. No, it's not. I apologize. It's spring. So I'm sorry. I don't know why I added a different time period. That's silly. But this is spring. And what I was trying to illustrate with this is that the black line is now completely off this dotted line that you possibly should be able to see in the images. And those solid black lines have completely changed now. And we now have this sort of flexible base generation that's there supporting the renewables. The renewables are doing most of the heavy lifting here throughout the day. And hopefully you can see the solar and storage pairing going on as well as the wind as well. And we do see curtailment as well. My final slide should be, if I'm correct, is how hydrogen all fits into this. So I talked about it being kind of a big area, and I didn't go into too much detail with it. But the model has to build these hydrogen facilities to produce the hydrogen. It has to build pipelines and use trucks to move the hydrogen if it needs to. It can either choose to build it remotely or buy off a market. And what we're trying to show in this is kind of just a big summary of all that. Is the yellow bars show how many terawatt hours of electricity is dedicated to producing hydrogen, and then the price of hydrogen nationally per kilogram. And so you can see it really drops pretty cheap in later years. And this is all based on NREL mid technology costs, just as an aside. So all the wind and solar and everything else is based on mid prices rather than the low prices, to be conservative about what we might need to do to electrify under different situations going on. And so this hydrogen actually supports a lot to do with the rest of the economy. And we're using around, I'd say, 10% of the electricity demand is used for hydrogen production. So I will stop there and allow others to ask questions or to move on. Thank you.
Okay, thank you very much. We have received a few questions, and we just quickly will run through them. Let me see whether I can see them here. Okay. The first question is, how did you model your electric vehicle demand profile?
Yeah, good question. We looked at conventional vehicles, ICEs, and got a lot of data from the US government on how much kind of gasoline is being used for vehicles. We then also went to the Department of Transport for vehicle miles traveled, both at state level and county level. And then I believe there's an MIT study as well that we dived into to look at how people are driving weekdays and weekends versus bank holidays, federal holidays, summer versus winter, each month broken down. And then we amalgamated that together to give us kind of the driving needs, miles driven. And then we then superimpose on that electric vehicle modeling, which I won't go into too much about it, but basically, how does a battery perform in different weather conditions? How do people behave in the vehicle in different weather conditions to keep a nice temperature in the vehicle? And then those are added together to give us the amount of kilowatt hours needed. And then for the input demands, we look at when people would actually plug in based on their electricity needs. And then we allow the model to do flexibility on that afterwards. So that's how we modeled it.
Okay, thank you. Next question. Any insights into the operational challenges in these futures? For instance, have you thought about how system operators will manage the dimensionality simultaneously with the uncertainty? And I might follow up also with a question. Your model, does that how does it deal with uncertainties? Does it have perfect foresight? How do you deal with disruptions, for instance, etc., and these things?
Yeah, so this model, we don't allow any loss of load at any time for any 5-minute interval anywhere in the contiguous US. We have forecasts that come in that we regularize against. The version I just showed you, we actually did just have perfect forecasts, but we can bring in forecasts to look at how that might change the choices. But it's a capacity expansion model out to 2050, so we don't have as much of the sort of disruptions that you talk about in terms of if we cut a transmission line or if load suddenly falls. We can run it in dispatch mode under many simulations when we've done the capacity expansion. For the operational challenges, we only really have the error bars that we put in terms of what the model sees as being the range of possibilities that it could get for each 5-minute interval, and then the range of forecasts that it gets. And so we can only use them together. But again, it sees all of this ahead of time. And so there is a lot to do with there being perfect foresight. And so even with the forecast, it still knows ahead of time that it's going to be perfectly wrong, if you will. And then finally, that's why we have a no loss of load. So we don't allow any load to be lost, because we think as a bare minimum, if you're giving it all this perfect foresight, you can't allow any time period to not be delivered electricity, because there's going to be other reasons why it might not be delivered.
I just noticed that the person who asked the question on operationality was not quite satisfied with your answer. So could you be a bit more specific there? So um, how, have you thought about how the system operators will manage the dimensionality simultaneously with the uncertainty?
Well, I think they'll just. I'm not sure I fully understand the additional dimensionality. They'll just see the load on the grid, right? So they will see that need of an electricity. They won't be controlling the sectors. They will be able to control. The model sort of assumes that the demand side will also be interacting with the operators, and so it'll all be done by computing. So that the model's automatically assuming that's how the additional dimensionality is being sorted, is through Internet of Things type technologies. But in the model, we're not really investigating how it will actually be fully operated. We're just assuming that it could be operated.
Okay, so if the person is not satisfied, still not satisfied, he can take contact with you. I'll leave. I have a few more questions, but I'll just allow one more, and we leave the other one for towards the end if we have more time. What factors are missing from your analysis? For example, I would expect a larger role for rooftop PV in spite of the higher costs. Issues would include local power reliability, independence, customer choice, privacy, etc.
Yeah, so in the modeling we do, we have a DER subroutine where we allow the model to build a hybrid system where we're modeling the distribution side and how it interacts, and then we're trying to lower the customer costs. In this role, though, because we're getting to deep decarbonization, unfortunately, just what wins out in the modeling is essentially the amount of energy that's needed to decarbonize the economy. And so the model's seeing that it's slightly more expensive for DPV, and we're producing less energy than we could by other resources. But like I said, this is just one example of optionality, and we can change it to look at a more distributed grid versus a more utility scale grid, more renewables and less renewables, and so on and so forth, to see how the costs might change. And they are going to be very small. The thing that we're really missing in the model, and that we don't model at all really, is that full just choice to do it regardless of how much it costs. Everything in the model is economic, essentially.
Okay, we'll leave it at that. Thank you very much, Christopher. Otherwise, I would have asked for a round of applause, but everybody's mic is muted except for a few people. But thank you very much. Let's move on to the next presentation then. That will be by Elizabeth Endler. She's Program Manager of Shell Engineering. And she brings over 15 years of industrial R&D expertise to her current roles as the Program Manager for Advanced Energy Storage and Principal Science Expert for Shell, based in Houston, Texas. She began her industrial research career in product development at 3M and provided research and technical support to Shell Chemicals before becoming a founding member of the Future Energy Technologies team at Shell in 2011. In that role, Elizabeth was responsible for developing and executing projects to demonstrate emerging low-carbon energy technologies, as well as supporting venture investments in areas including energy systems integration, energy storage, and future chemicals. A chemical engineer by training, she currently leads an international team, manages a global research portfolio of over 25 external collaborations focused on energy storage, and she serves as senior technical advisor for programs related to electrification of the mobility and industrial sectors, energy system integration, and energy storage. She holds a bachelor's from the University of South Carolina and a PhD from the University of Wisconsin-Madison, both in chemical engineering. And with that, I turn it over to Elizabeth. Please, you have the floor.
Thank you so much for that kind introduction. I really appreciate the opportunity to talk to everybody today about some of the thinking and work that we're doing around flexibility in a number of different sectors at Shell. I also appreciate the introduction in terms of the topics from both William and Christopher. I hope to touch and dive into a little more detail, particularly from the industrial sector perspective. So first and foremost, please don't take this as investment advice. This is a technical presentation, and I'd like to just share some of the highlights with you. So when we look at electrification and we look at the energy sector broadly and how are these things changing, Shell has a history of over 40 years looking at scenarios in terms of how energy use can change due to a lot of different drivers and factors over time. And what you're seeing from this particular chart is a key view that when we look out as we progress toward the end of the century, the central role that electricity really starts to play in terms of energy consumption. And by definition, also primary energy supply as we look at that. And that's really driven, again, by the challenges around more people, more prosperity, and lower carbon. And when you start thinking about electricity as your primary energy source, it really starts to change the paradigm. Electricity is, as we've talked about, very high quality energy. And up to this point, when we have had to convert fuels into that electricity, it's very dear. It's very, purpose-driven in its use and things. We don't want to use it for a lot of things because it's very costly to get it to that form. But when you start with solar, when you start with wind, and you've got additional choices now, especially as we start thinking about industrial conversions, whether you go to hydrogen, whether you go to higher grade chemicals, or whether you go to hydrocarbon fuels, you've got a lot of optionality at the price of efficiency. And so then the question becomes, how do we really start to think about this balance and really start to drive electricity as our primary energy source? So from an energy company perspective, I wanted to just give this snapshot because typically, again, most people know Shell best for its activities in the oil and gas sector, particularly as we talk about, say, items 1, items 2, item 5 on this particular chart. I'm going to talk more about box 3, this manufacturing and energy production today, and when we talk about the industrial sector. And more specifically, we'll talk about both the power generation side of things as well as the production of products, whether it's petrochemical, refined products, liquid products, and things of that sort, and how electrification starts to fit into that sector as well. To go a little bit more into depth around chemicals, because I do find this to be, as a chemical engineer, very helpful in terms of framing what types of options, what types of requirements are needed as we think about process designs, process engineering, and other pieces, to really start to say what are the building blocks, how do we go from feedstocks all the way through to finished products. And the other point that I wanted to make on this particular chart is we have Shell has participation in a lot of the points along this value chain. And so as a consequence, each of these has different process lineups, different considerations, different customer bases, different operational strategies, things of that sort. So we really have the opportunity and the need to think about these types of challenges very holistically, whether it's within chemicals, within electrification, or the intersection of the two. When we talk about electric power, last June specifically, Shell came out and explained its ambitions and activities in the integrated power system to the capital markets. And so to illustrate some of the areas where Shell is currently playing, to give you, again, a sense of what are some of the technical market commercial considerations that we might keep in mind, showing this diagram here where you've got everything from generation, kind of in the top left, energy production, whether that's solar, whether that's onshore wind, whether that's offshore wind, whether that's usage, whether that's trading, whether that's optimization, all of that comes into play. And while I've listed a number of investments and acquisitions that have been made over the past 5 years, what I also wanted to mention is that Shell actually has been active in the power sector for over 20 years, particularly in North America, through both onshore wind operations as well as electricity trading and supply. So in terms of just highlighting a few of these investments and acquisitions, to give a sense of the scale and the different dimensions that we think about, you can think about, again, large-scale offshore wind. That's the Borsela 4 and 3 in the North Sea off the coast of the Netherlands. You can think about large-scale solar. That's Silicon Ranch in the United States. You can think about residential energy storage and optimization. That's Zona in Germany, 2019. You can think about electric vehicle charging, New Motion in the Netherlands, Green Lots in the United States, et cetera, et cetera. So just to give you a sense of the range of options and points in the value chain that we are looking, as well as the challenges that technically our organization is looking to solve. To talk a little bit again about the concept of time scales, length scales, size scales, and how these things intersect. For me as a chemical engineer, when I first started working in the electrification sector and really looking around energy system integration, one of the things that really struck me was the fact that when we talk about these operational timescales in the electric grid and the power sector, you really also have a lot of analogous timescales, length scales, size scales in manufacturing as well. So when you're looking at whether it's design of a new plant and you're taking things into account from a very long-term perspective, what is the demand for the product, then more granularly, what does the plant lineup need to look like, how does each unit operation need to line up, and things of that sort, you're able to really work in a very analogous way as we see some of the system capacity pieces, whether we're talking seasonality and weekly, daily, or even down into the granularity of sub-minute type of operations. When you're looking at a process, again, you're trying to optimize and control at these shorter time scales, whereas when you're looking at larger scale dynamics in the industry overall, you're much more on the left-hand side. So again, when we think about flexibility and this capacity, especially when we're talking about variable renewables and what do we do, historically, when we first started looking at this, we took very much a power sector only approach, and that's shown on the left here. And this is essentially just a very conceptual merit order type of diagram for flexibility resources, focused on, again, conventional types of levers that you might choose to deploy when you need them in a given market, in a given region, in a given ISO, et cetera. And so when we look at that and we see the various pieces here, the sizes will be different, the amounts will be different, the costs will be different depending on the market, but it gives you a sense of the different levers that you have. As we've talked through the introduction and other things, we now are starting to look at having many more additional levers at a much bigger scale. And so as an energy company, when you start looking at these different levers and pieces, they all intersect with areas that we are historically supplying today. And so they become very interesting very quickly when you start to say, how do these pieces all start to fit together? To give you an example of what we've looked at from an energy storage perspective, again, staying within the confines of traditional systems, back to this multiple scale, multiple consideration piece. And going from large scale on the left down to small scale on the right, we've worked on projects, for example, wind integration in West Texas, really looking at what happens when you try to co-locate, when you're looking at multiple use cases, use case stacking. What does that look like for wind, a particular onshore, with some of the dynamics that were just talked about in the previous talk. We also look at what's more relevant for commercial and industrial applications. So through our microgrid at Shell Technology Center Houston, we look at the role of solar and different types of storage, flexibility, coupling with natural gas, building loads and things of that sort, to really try to look at the various dynamics that are taking place at that scale. Then finally, in also looking at the coupling of heat and electrification, we have our residential living laboratory in the Netherlands, where we actually have a small townhouse that we look at all of these different options for residential applications. So again, this combination of time scale, length scale, size scale. Again, industrial electrification, not new. Through some research I was doing previously, ran across a paper from EPRI in 1983 talking really about these same questions that we're grappling with. What is it? How can we scale it? What are some of the critical technology challenges that we need to overcome? And what I'd argue now is that what we're really seeing is commercially the opportunity to really start to drive electricity costs into a space where these questions really become viable. So I've listed some of the sectors that and their concomitant values that you'd need to see, pricing strategies for electrification. And what we're able to see in the next slide is that, in fact, we're actually starting to hit some of these at the low end. So again, this is from Bloomberg New Energy Finance. When you're talking about getting into that $20 to $50 a megawatt hour range, we're starting to see that for a number of different options. But for industrial power to really be able to move the needle in some of these places, we still have very much a strong regional difference. You can see differences on the left in particular for industrial, as well as what we see for residential. And so trying to get some of these things matched up in terms of what we're seeing for wholesale versus what the industrial customers are paying, still to be worked out how we can really take advantage of this. I've spoken a little bit about this already in terms of when you do have solar, renewables, things from that standpoint, how do you make these choices as you go up the level of complexity in the value chain? And so when we talk about today's energy mix and where can we start to really look at electrification, we start to see a bit more where these different fuels are used, where electricity is already being used. And I think a slide that also helps tell the story is our next one, where in particular on the left, we're talking about U.S. energy use by sector. Everything below the black line is electrified already. Everything above is not. And so we really see industry and transportation being strongly behind the built environment already. And when we dig a little bit deeper into what's going on here, we start to see some real opportunities in terms of what fuels are already in place and where electrification may be able to play a role in different fuel displacements. So again, I talked about electrification not being new. When we go back and we look at industrial sectors and applications, process units in particular, where we have used electricity for a number of years, it's A, really long time, and B, these are areas where we've really started to unlock a lot of the flexibility, and more of that will be shared in the following talk as well. And so one of the key questions that we keep in mind from a technology perspective is when you take what has been done where electricity has really played a significant role in the past, how do we now really start to think about that for some of these next types of chemicals that really help to form the backbone of what we're doing going forward? So heat is a huge one. It was alluded to in some of the other discussion points, but process heating is actually a really big lever as we look at the industrial sector. And this really moves into different types of sectors, low, medium, and high grade heat. And the good news is that from a just potential possible feasibility perspective, electricity really is able to drive and deliver a lot of the temperatures that we need. That said, in terms of doing this in a very practical, robust, long-lived operability perspective that we're used to in the traditional process industries, there's still a ways to go. And on the right, I'm showing some different process technologies that have been summarized in the literature for different types of high-grade heat. On the left, I'm showing some examples in terms of where you could potentially start to think about how you approach and where deep research is needed to really be able to go further into the industrial sector. A lot of this, as has been alluded to before, can be also put to use in terms of where are we potentially going in terms of synthetic energy carriers, and in particular dense energy carriers such as, say, power to liquids, solar fuels, and things of that sort. This is an area that Shell has active research and development work already ongoing. And again, coming back to where does electrification fit in, you can look at capturing, you can look at conversions, you can look at the hydrogen and the various downstream processing as well. So this is a more integrated process view of where some of these building blocks start to come into play. Another point around hydrogen that folks, we've talked a little bit about before, in addition to actually having hydrogen as a way to accept electrons, it could potentially also be a way to improve flexible demand as well. And so this is actually a study from Endler just using to illustrate the concept that was done several years ago, where they were comparing PEM versus alkaline to really understand, do these particular pieces of process equipment have some of the flexibility that we could potentially use going forward to help monetize and or just better use the renewable electricity that we have on the timescales that it's delivered to us. And really, the big answer of this is yes, you absolutely can do that. Certain technologies are inherently a little bit more able to do this, but in general, you're able to meet the demands of the market. One of the big open questions, though, and this is true for a lot of process technologies, and especially at the unit operations level, is what happens over the long term? Because when we typically look at the chemical industry, you're talking about assets that are in place for a number of years, sometimes even longer than the electric power industry. Yes, through retrofits and turnarounds and things, you'll upgrade and do some things. But overall, you're really looking at a very long-lived type of asset. And so the question around what does this mean for these new technologies is still very much one that is under research. Finally, just wanted to tie some things a little bit back together in terms of this process and electricity piece. The articles on the left are from the chemical process optimization literature, and really started laying the groundwork in the early 80s and throughout today to really talk about this concept of resiliency in process design. So the idea about being flexible, operable, and controllable across these different timescales, and what does it really take to make that happen from the point of process design all the way through to build and operation. And one of the things that I really wanted to highlight, we've talked a little bit about demand response, and one of the chart here really starts to show, as you try to really implement some of the barriers and challenges that you can run up against, and how theoretical and what is realized are often two very different things. And to really get back to this flexible, operable, and controllable piece, what we've seen so far in most places where that's been implemented, the role of storage really comes into play. And in the power sector, we typically think of power storage, but this concept of how do we use not just maybe hydrogen, but also some of the other embedded flexibility throughout the process industries to help manage and balance some of these things is a current interest and area of active research as well. Finally, just again, wanted to show brief overview from the Energy Transitions Commission. This is from their Mission Possible. If you're not familiar with sector coupling, this is, I felt, a really useful way to kind of help summarize it as a snapshot. So again, it comes back to this direct electrification, the role of hydrogen and other energy carriers culminating with syn fuels to really help show not just the industrial sector, but also some of the other sectors that we've talked about in terms of including transport. So finally, just to wrap up, wanted to just highlight the fact that we do actually have some unique synergies between the chemical process industries and electrification. Sometimes not always obvious, but they are in fact there, and really excited to be able to share this with you today, because really felt like this topic was an intersection of quite a lot of things that I've worked on over my career, and it's just an incredibly exciting area. Talking also about the different things that we have the potential to play key roles in products, process, and services. And finally, just one last thing to add that was just actually announced today. Our CEO, as part of our Responsible Investor Day, which was earlier this morning, Central European time, we announced our ambition to be net zero emissions from our own operations by 2050 or sooner. And one of the big levers that was mentioned was zero and low carbon electricity and steam, in addition to hydrogen and biomass to help support that. So for me personally, this is a very exciting time, and really appreciate the opportunity to share this with you, and want to also acknowledge my colleagues who have helped contribute to this work. Thanks very much, and happy to take questions.
Okay, thank you very much, Elizabeth. There are indeed some questions. First one, what technologies are you looking at for electrification of ethylene production? Electrosynthesis from hydrogen and CO, question mark?
Yes, so a lot of the work that we do in our research department looks at electrochemical conversions of CO2 through a number of pathways. So that from an electrification route, we see that as one. We also, in particular, have that looking coupled to some of the work that we're looking at our synthetic fuels through direct air capture, and again, conversion through different technologies. leveraging our history in gas to liquids in a lot of cases as well, because a lot of these go through some of the similar intermediates. Certainly when you change from thermally driven routes to electrochemical, there are some changes, but we certainly are investigating different process lineups that can take advantage of a range of feedstocks.
Okay, now I read this question literally. It said hydrogen and CO, but I think what was meant was CO2. I think so, but
well,
okay.
it's. I mean, see, that's you're talking about syngas. So syngas as a key intermediate to being able to go forward, absolutely, is huge, especially when you start with CO2.
Yeah. Okay. Next question: will huge reductions in profits of the oil gas sector, which is the main driver of Shell, due to the current low demand and increased supply, reduce investment by Shell in these initiatives in power systems? If not, is Shell changing its business model? So it's a bit of a thorny question, but okay, I'm posing it anyway.
So what I will do actually is I'll direct for more detail, because we actually have quite a lot of information around our strategy on electric power and the commitment to investment and how things have changed over the last 6 weeks on our investors site. So our public site, www.shell.com/investors. I would direct you to a lot of the detail there. In short, we absolutely are taking short-term actions to support our framework of being a world-class investment case, being in step with society, and thriving through the energy transition. Those are 3 pillars of our strategy, and they remain unchanged. So from that standpoint, we are very much committed to our business strategy that we talked about in terms of electric power being part of our business. In terms of what is going on in the short term and things like that, again, I direct you to the specific actions that were mentioned in late March around what we're doing around capital spend and things of that sort, and how that's being looked at.
Okay, now that leads me also to then a follow-up question. What does guarantee that Shell, by looking more at the electric power sector, would be more successful than, let's say, 20 years ago? Because indeed, as you said or alluded to, Shell and BP were one of the pioneers in the early 2000s in the renewable sector, but they both gave up. Is it the whole different thing that renewables have become more cheaply, and that there is now the drive to decarbonize, to fully decarbonize the overall energy system?
We have absolutely seen just a tremendous amount of change in the last 10 years as the energy sector has evolved. And I think I would again come back and point out, when we look at our various scenario planning tools and capabilities and what is being seen in the markets, again, from a business opportunity perspective, whether it's policy and regulatory changes, all of these things have come together to lead us to the points that we've gotten at this point around where our business strategy is. Absolutely. As I mentioned, we've been in onshore wind for over 20 years, so that was part of that first wave of what we've done, and we've certainly taken a lot of the information that we've collected over those time periods and applied it to what we're doing now.
Okay, then I'll allow 2 more here. Then how do your efforts relate to work by Shell New Energies? That's probably related to the previous one.
Yes, so I actually, the group that I sit in is what's called New Energies Research and Technology organizationally. So we are the technology group that works very closely with our Shell New Energies business. So it is part of the integrated effort across the company.
Okay, and finally then, can you elaborate on the relevance of hydrogen for power-to-power and the advantages compared with other power-to-power storage options?
Yeah, no, it's a great question. And power-to-power, as I mentioned, you lose on the efficiency side, but certainly in a number of locations, people are looking at how can you decarbonize natural gas through hydrogen, or how does hydrogen potentially stand on its own? And so there are some potential advantages, particularly if you can get the geographic distribution correctly. And so when we look at the options across what you need to think about for integration and storage, we absolutely see various types of storage ranging from everywhere from electrochemical through thermal, mechanical, all the way through to chemical, and this type of molecular type storage. And we do see the fact that these chemical storage, whether it's hydrogen, whether it's something else, there is value in those chemical bonds. I mean, that's how we've done electricity storage to date for so many years, just on the front end.
Okay, thank you very much. We actually have a few more questions, but regrettably, time is running. When we have a little bit of time left, we can still come back to that. Otherwise, I'll advise those who have asked a question to get in contact with you directly. Thank you very much. We appreciate really your presentation. And now it's time to move to the last presentation of today. That's by Michael Baldea. Michael is Associate Professor and Frank Little Jr. Centennial Fellow and Undergraduate Advisor of the Chemical Engineering Department at the University of Texas at Austin. He obtained a PhD in Chemical Engineering from the University of Minnesota. And prior to joining the University of Texas, he held an industrial research position with Praxair, which is currently Linde. His research and teaching interests include the dynamics, optimization, and control of process and energy systems, areas in which he has co-authored 3 books and over 160 peer-reviewed journal and conference articles. He received several awards. I'm not going to name all of them, but there were a few special ones from the American Institute for Chemical Engineering. I guess that's what AICHE stands for. And also the NSF Career Award, amongst others. Michael, you have the floor, please.
All right. Thank you for the kind introduction, and thank you for the invitation to participate in this conference and present some of our work in front of this very distinguished audience. So I'm very excited to be here. I really regret not being able to participate in a physical version of this conference, but maybe in the future. I think that would be very exciting. So I will talk about some of the work that I guess my talk will segue very nicely to the other 2 presentations before, excellent presentations before by Christopher and Elizabeth. And I will talk more specifically about how chemical processes and process engineering interact with the grid and the benefits that they can provide in terms of flexibility. So I think I was told that I need to consider this as more of a tutorial presentation in a sense. So I started with what's the most basic thing, what's a chemical process? So the chemical process is a system that can turn any kind of raw materials, and these are often harvested from nature, such as gas or coal, to some value-added products. And the reason or the way that happens is through the combination of physical transformations and or chemical reactions. So there are plenty of examples that you're familiar with, and umpteen examples that you probably never heard of. These have been mentioned before: so oil refining, aluminum production, ethylene production, glass furnaces. These are all actually chemical plants, which affect some transformation on the raw materials to obtain products that are value-added and hopefully sellable. And the statistics speak for themselves. These are data pulled from the EIA. They indicate that the chemical sector is actually really the largest consumer of energy and industrial consumer of energy in the United States. And I would place a lot of the food processing, paper processing, or paper production, some of the iron, steel, and aluminum within, let's say, the spectrum of chemical processing. So we are a big consumer of energy. Now, of course, the question comes, where does this come in, or does it fit in terms of interacting with the grid? So there's, of course, the chart on the right, which is, again, the energy outlook. which indicates that in the industrial sector is about, let's say, roughly 1/3 currently of, or maybe a little less than 1/3 of electricity consumption in the country, and will perhaps keep its proportion going forward. So you see that out of that energy consumed by the chemical industry, of course, a lot of it is electricity. So where does electricity go, right? These chemical and physical transformations are affected with external energy output. So the basic example is that you would use electricity to generate heat, so that an arc furnace would do that. We don't necessarily want to do like resistive coil heating, but microwave heating, for example, has been explored. Usually that kind of heating has been deemed too expensive in the past, but it doesn't mean that it won't become interesting in the future. Electricity is also used to support certain types of transformations that just wouldn't be possible otherwise. So electrochemical reactions, and that's, for example, electrolysis to produce chlorine or aluminum. And then there's also the use of electricity to generate work. So compression is a typical example, and we'll talk about a few plants where compression is a key transformation. So each of the use cases of electricity in the chemical industry, from the perspective of interacting with the grid, comes with certain challenges and certain opportunities. In my perspective, these are related to three elements. One of them is the magnitude of the load. The other one has to do with the response time. And then the third one has to do with location. So in terms of magnitude, we already say that chemical plants are, in general, large and concentrated loads. So that could be either a positive or a negative, depending on the perspective that we take. In terms of response time, chemical plants become challenging, and this has been pointed out earlier, because their evolution spans multiple time horizons. And we really have to be very careful as to which of those time horizons we access or exploit in interacting with the grid. And then the location has already been touched upon before. The same chemical plant will have a different potential or benefit from interacting with the grid depending on where it is located. And location so far has largely been driven by access to raw materials as well as energy, but the primary consideration was not the interaction with the grid. The design so far regarded chemical plants as takers of energy or as pure loads. So with that in mind, I think we could go ahead and discuss a few examples just to put things in perspective. So I'll start with talking about magnitude. So I'll give three examples here of plants that have a heavier light on electricity. And actually the first two have an almost exclusive use of electricity as the energy source. So if we think of air separation is not only useful for providing oxygen, argon, nitrogen, which are then used as utilities in other industrial sectors, but it's also a pretty interesting partner for interactions with the power grid. So it's a cryogenic process, which means it's done at very, very low temperatures, and it relies on liquefying air from the atmosphere and then distilling this air to produce the three components that I mentioned before. So to give you an idea of what a plant like this consumes, so to make a ton of oxygen, it's about 350 kilowatt hours per ton. And then this is not the typical capacity, the 5,000 tons per day, but there are plants that go up to that capacity. So I'd say for an oxygen plant connected to a steel mill, you're probably looking at 150 to 300 ton per day facility. Chloralkali is the main source of chlorine for various other purposes. So for example, the production of polymers like polyvinyl chloride, for water treatment and so on. And the way it's done is through the electrolysis of a solution of table salt or brine. And then that has caustic or sodium hydroxide as a byproduct. So here we're looking at about 2,300 kilowatt hours per ton of chlorine produced, and the plant can be up to 2,500 ton a day. So we're looking at this sort of 200 plus megawatt load. Then we're looking at glass. So glass is an interesting example because glass furnaces can be hybrid. So they are both gas-fired and electric heated. So these systems can sort of balance between the natural gas and the power grids to some limits. So here, gas firing for this example here is predominant. So now we're looking at about the 9 megawatt load. And each of these are chemical plants, but they have very different characteristics. Like I mentioned, the air separation unit on the left is sort of a monolithic item. We'll talk about its time constant in a little bit, but it can only move, let's say, in sync, so there's no modularity there. On the other hand, the chloralkali plant has some interesting properties in terms of speed of response and as well in terms of modularity. So part of it can be shut down. It consists of many cells that operate in parallel. And then with the glass furnace, there's this interesting feature of being able to balance between using natural gas and using electricity, at least for a little while, in order to provide services to the grid. So going from magnitude to the speed of response, I think we really need to consider exactly how chemical plants operate. And Elizabeth has already hinted at this in her presentation. Actually, the two of us had a brief discussion to coordinate what we're going to talk about, and I really appreciate that. So the operation of chemical plants is a highly hierarchical affair. So there is a business decision layer, which deals with what to make, when to make it. So these are production planning and then production scheduling. And these business drivers do take precedence, right? Because there's orders to be fulfilled and product to be delivered. So there has to be a relatively strong financial incentive to perhaps interfere or override those decisions when we talk about thwarting or diverting the operation of a chemical plant to interact with the grid. Then there's another aspect here, which is control. So what these business decisions result in is kind of a set of trajectories or targets or set points for a control system. And the control system has a crucial role in, first of all, meeting those targets, but also in maintaining the safe, stable operation of the plant, in particular in the face of disturbances. So it is, in my experience, interacting with different chemical industries, it has been very clear that they're not willing to compromise in any way on the safety of the operation or the quality of the product under any circumstances, and that includes interacting with the power grid. So these decisions are made over different time scales. So planning can take a very long time horizon into consideration. So that could go for months. And this does, by the way, does not include capacity planning for the construction of new plants. It just has to do with the operation of existing facilities. Scheduling is something that's, let's say, more shorter term, so it can look into days or hours. And then the control system is something that acts in the here and now. So this hierarchy of timescales also kind of corresponds with the dynamics of the plant itself in many ways. So if we think of when and how a chemical plant would have to respond, we have to think about how it could interact with the grid. So the most frequent way of using a chemical plant in the operation of the grid is through this price-based demand response. So on the left, I'm giving an example of price data from ERCOT. So this is admittedly an extreme day when electricity prices went up by, say, a factor of almost 20 during the mid-afternoon because of a spike in demand. So how would one exploit this kind of price profile? Well, if you're a chemical plant, really what you want to do is to produce less when electricity is expensive and produce more when electricity is cheap. So Basically, what would happen in a production scenario where these prices are known or can be anticipated is a manufacturer could decide to up production during the early hours of the morning when demand on the grid is low and electricity is cheap, make more product than actually needed at that particular moment, and then store it, and then eventually drop the production rate when electricity is expensive and use that stored product to meet demand. So there's a few things here that we need to appreciate in terms of chemical process operations. One of them is that interacting with the grid and taking advantage of electricity price fluctuations requires frequent changes in production rates or the type of product that we make, and making use of electricity storage. So we have to assume that, first of all, we can make more product than we need, so there's some excess capacity available, and also that this excess product can be stored safely for at least a little bit of time. So this requires then a tight coordination between production scheduling, which is a business decision, and process control, which is a decision that's often made just at the level of the plant. And ultimately what this amounts to from the point of view of serving the grid is that we store electricity in the form of chemical products or chemical bonds, as has been pointed out before. So we don't aim to break these bonds to regenerate electricity per se. What we want to do is make these bonds when it's cheaper to make them, and then just use them as is later. So the question is, how quickly can a process actually respond, right? We need to move relatively fast, right? These peaks in prices are sometimes pretty short-lived. So if we look at an example of an air separation, now I'm going to delve a little bit more into what the structure of a chemical plant looks like. Basically, the only consumer of electricity here is a compressor. So we need to bring air up to pressurize air to about 6 bar in this case to be able to liquefy it. And the liquefaction all occurs internally based on exchange of heat with cryogenic products. And then the distillation occurs in this distillation column.
Michael, can I interrupt you for just a moment? We're getting a lot of interference on your audio. Could you perhaps try it?
I'm not sure what I can do here. Maybe how bad is it? Should I call it?
It's already better.
It's already better? Okay.
Yeah.
Okay. I will. Is this good then? I'll just hold the microphone right very close to me. Is that okay?
Yeah, I think it's better. Yeah.
Okay. I apologize. And thanks for pointing that out. Should I continue?
Yes, please do.
Okay. So talking about air separation, why is this interesting? So air sep makes up for about 2% of U.S. electricity demand, industrial demand. And the way we can store electricity is or energy is we can switch between making a gas product, so gas nitrogen, versus liquid nitrogen, which is easy to store in a cryogenic tank, and then evaporate that liquid nitrogen to feed the pipeline of gas nitrogen to customers, which is here at the outlet of the plant, right? The dominant time constant of this process is in the order of hours. So there's some industrial data here on the bottom left that show that we can change the production rate for a plant like this very quickly. So that also changes the load that these compressors place. But the purity of the product, so we aim to make nitrogen that is about 6 or in the order of parts per million purity or concentration of impurities. That takes about a couple of hours to settle back to a steady state once a change is made. So that means that if we follow hourly changes in day-ahead electricity prices, we may never actually reach a steady state in terms of product purity, so we have to be extremely careful in the way we manage the operation of this plant. So what the implication is of what I've said before is that in order this type of plant can participate in activities like price-based demand response, and we've shown in several analyses that that can lead to about 1 or 2% reduction in the operating cost for the plant, which for an industry that has been around for more than 100 years is quite significant. And this basically means there's no further investment in assets. It's just a change in operational strategy. These industries can also provide interruptible power, so they can get a call from an operator, grid operator, and completely shut down. This will have to be really worthwhile in terms of what the premiums are for this, simply because the time it takes to restart the plant can be up to a few days. So talking again about dynamics, we can look at chlor-alkali. Again, this is about 2% of U.S. electricity demand as well, so it's also a needle mover. And the storage strategy here is similar. So we can take gas chlorine, liquefy it, store it, and we can make more when electricity is cheap, and we can make less expensive. But the interesting thing here is that the dynamics of this plant are almost instantaneous. So we can manipulate the current density through the electrolysis cells very easily. The dominant time constant of the plant is still in the order of hours because of thermal inertia, but from the point of view of modulating operation and shutting cells down, this could be very easily done. So this type of plant can also participate in price-based demand response. We've noticed in our studies that because it's a much nimbler system, the savings here can be quite significant. And then it can provide frequency regulation, interruptible power service, unlike the ASU that I discussed before. Now, one of the last considerations I want to cover in terms of what the chemical process can do in interacting with the grid. This is a ongoing question. It's research that we're still carrying out. I think we need a lot more understanding of how we can utilize a chemical plant as a grid resource as opposed to sort of a unilateral self-directed demand response resource, or price-based. So keeping in mind that the magnitude of the load, the dynamics of the load are important, the location of a chemical plant will really define the impact on the grid, right? So looking at this very simple reliability test system that was introduced by IEEE 40 years ago, we can fathom that placing a chemical plant load in at different buses is going to make a big difference in the impact it has on the operation of the grid as a whole. So things that need to be considered is how we can help with congestion and how we can deal with variable generation rates from renewable energy. So there's some wind turbines that are included in this example. We also need to think about who actually makes the decision as to how a chemical plant operates. And that's a key question that as of yet does not have a good answer in my mind. So if we think about independent operation by the chemical plant operators versus cooperative, where the grid operators would set some of or make some of the production decisions, this makes an important difference. There are open questions regarding how we actually represent the dynamics of a chemical plant in power system modeling, and that immediately ties into privacy and how much information would a chemical plant operator be willing to give up or to share with the grid. This has to do a lot with this. These are not generators, right, where all the information gets posted, but there are chemical plants. There are many competitors out there who could potentially use that information for their own purposes. So to us, it remains an open question as to how cooperative operation could be implemented without jeopardizing any kind of sensitive business information. So it's probably time for me to conclude. I think that I managed to convey that chemical plants are actually a big player in industrial electricity use. They can support grid operations, and they do, but we have to be mindful of several things that are particular to the chemical industry. One of them is safety and product quality, which are critical to process operations, and they will take precedence over any other initiative. Their dynamics are different, and a chemical plant is sort of a misnomer. There are many types of chemical plants, and based on the operations they affect on the raw materials, they will have different dynamics, different response times, different constraints, which all need to be accounted for when we envision any kind of interaction with the grid. And finally, the plant location in the grid topology will also bear a big influence in deciding how to support the grid. So there are open questions that remain here. What should be the optimal power flow problem or scheme for fully exploiting a chemical plant connected to the grid? How much control are operators willing to do or to give up? And then also, how do we share the spoils equitably? So what pricing schemes could be offered to chemical plant operators as an incentive in order to engage in any kind of support scheme for grid operations? So with that, I'd like to close. There's a number of people that I'd like to think of, and then also there's some funding sources that have been key to developing our results and really supporting the way we shaped our thinking about this topic. So with that, I'd like to close, and thank you for your attention. I'd be happy to take questions.
Okay, thank you very much, Michael. Let me see that I can look at the question. Yeah, there's a question. Both chemical engineers, so your predecessor, so Beth and you focused on short-term flexibility. What about seasonable flexibility? For instance, could you produce product A for 6 months and then with the same plant produce product B that requires less energy, or produce no product, something like that?
That's a good question. You can. The question is to find, so in principle, the answer is yes. Now, the question is to find those two products. And I can't off the top of my head think of an example right now, but I'm sure we could try to identify them. So you could make different grades of fuel, for example. I'm not sure if they would use different types, different levels of energy, or that much different. The other, if you could make something one season and do nothing another season, that's possible, but again, you will have to have double the capacity and the ability to store all that material. So, in principle, yes, but it depends on some physical limitations. Storage is not very expensive for many chemicals, so that's something to consider. But increasing capacity beyond the design capacity is difficult.
Is not very justified. You have to look at it on a case-by-case basis. You have certain constraints like product quality and safety that you cannot compromise. And then my question actually is, how important then is the pricing scheme? So I would think that given those constraints, that price will be very, very important as a result.
You mean for electricity or for the chemical product?
I mean for electricity. So the price, the price signal, the electricity price signal.
Yes. Yeah. So like I said initially in the slides, I said that there's got to be some economic incentive to doing this. So the pricing scheme is indeed very important. The way the chemical plant exploits any kind of pricing scheme is by having some excess production capacity. So if your design capacity is X, then if you have actual, or not design, but the nominal demand is X, and you design the plant for 1.1X, your swing capacity, so to speak, is that 0.1. So whatever it costs to put that 0.1 in place has to be compensated for by the price that you get, or the reward that you get.
So do I understand correctly that this will also then depend on the long-term planning actually for new investments, that you might then do your investment a little bit differently, let's say 10, 20 years from today than you would have done today, in order to assure that you can play in that market? Or is there just too much uncertainty in the long term as far as the price of electricity is concerned?
I'm not sure. So what you're saying is true and would make sense. And I'm not sure that in many cases, or at least not in the industries that I've interacted with, this particular interaction with the grid is right now accounted for as a stable and key revenue stream, right? So I think it's regarded in many ways as sort of a bonus right now. But absolutely, if firmer information were available about how interactions with the grid can be beneficial and be accounted for long term, then that should be a consideration in planning capacity.
Okay. Well, thank you very much, Michael.
Thank you.
I think it's about time to wrap up. We're running out of time. We actually have gone over time already, even with only 3 presenters, but that's what happens when they're all very interesting. So I would like to thank the panelists for their presentation today, and thank, of course, all of you for your participation, and also those who have asked the questions. Let me also thank ESIG then, and especially Charlie and Ryan, for making those virtual sessions possible, regardless of the Corona situation. I'd like to remind you that the next Tucson webinar, session 8 on ESI planning, optimization, and modeling techniques will be held on Tuesday, April 21st at 2 p.m. Eastern U.S. time. You can find the full schedule of upcoming sessions on the ESIG website. And thanks again for your participation. Stay safe, and we look forward to seeing you for the next session. And please stay healthy as well. Thank you all very much. Bye-bye.